So today what I want to talk about is the perceptron, which is the thing that you remember in the first lecture we talked about, this remarkable thing from 1958 that was going to walk, talk, perceive the world, change everything, right? So this is the seed of modern neural networks. And so today's lecture and then the two lectures next week are going to basically cover the development of neural networks from like this very simple idea to kind of an introduction to modern deep learning. One thing to keep in mind is that we have a whole separate deep learning course at RPI, and so I'm not going to talk too much about that other than what we talk about like next Thursday. But by the time we're done with these three lectures, you should have some sense of what neural networks are, and homework 4 will have you using them to do some simple tasks, which I haven't written yet, but that's on my list, right? So I'll say the perceptron and, kind of like intro to neural networks. So far we've talked about several different ways of designing a linear classifier, right? Meaning that I've got a bunch of, points on one side, points on the other side, and I want to find the best line that separates them, right? So we talked about, Fisher's discriminant. We talked about support vector machines. We talked about logistic regression. There are lots of ways of doing that. And so today we're going to talk about the perceptron, which is yet another way of doing it, but in a way that we're going to kind of extend into neural networks. So the setup is the same, right? So the idea is, linear classification. And the setup is that I have a model. I have this F, which I'm going to talk about in a second, weights and features, right? So again, just to refresh your memory, because it's been a couple of days since we've had a lecture. So again, these X's are my input features. This phi is basically some sort of a nonlinear transformation. This W are weights. And so for the moment, I'm going to kind of assume that the weights are including this bias term, right? So usually there's like a plus W0. Let's assume that one of these phi functions is equal to 1 so that we don't have to worry about that. This F is what we're going to call an activation function. And then this Y here is basically our model. And so let's suppose that my target classes are given by, instead of X's and O's, we have some plus 1s and minus 1s, okay? And so what is this F going to be? In today's setup, this F, this activation function, is just going to be basically the, sine of t, which is equal to plus 1 if t is greater than 0 and minus 1 if t is less than 0, right? So our setup is that we're trying to get our model to predict the same signs as we have in the input-output training data, right? Okay, so this is the setup of the perceptron, right? So now the question that we have to ask is, like, what is a good loss function to use for the situation, right? Well, since everything here is binary, it kind of stands to reason that we want to design a loss function that has to do with, how many mistakes did I make, right? If I have, if the true output is plus 1 and my model predicts plus 1, everything is fine. If the model predicts minus 1 instead, I want to do something to kind of move the model over to be closer to what the true target value is, right? And so the idea is that similar to support vector machines, we don't really care about points that are well classified or correctly classified. We only care about points that are misclassified, and we're going to try to learn how to improve our classifier, okay? So kind of the, loss function is basically related to the idea of we don't care about correctly classified points. Only misclassified ones. And we want to kind of penalize points according to how far off they are, right? So in some sense, if I'm trying to draw a straight line through the points and I have an O over here, I kind of care about, well, how far away is this O from the decision boundary, right? If it's really close, it shouldn't get too much of a penalty. If it's far away, it should get a pretty big penalty, right? And so, again, this is kind of like what we call a hinge loss, which I think I talked about earlier. So we want to penalize points, or penalize bad points in proportion to how how far away they are. And this is sometimes called the hinge loss. Kind of the idea being that, if things are on this side of the line and life is correct, my loss is 0. If my classification is incorrect, I kind of have a penalty for, the further you are away from the line, the worse your penalty gets, right? And this is why it's called a hinge, because it kind of looks like a hinge. Okay, so let's kind of try to make this a little more mathematical. So the idea is that, again, I'm assuming that the target classes are +1s, -1s. My model is also going to produce +1s and -1s. And so in the best case scenario, things are well classified. What do we have? So ideally, for class 1, what I want is that, the target is equal to +1, and I want the W transpose phi to then also be greater than 0. That means that my Y will be, +1. If I'm in the other class, for class 2, and T equals -1, then I want this thing to be less than 0 and the output to be -1, right? So if I put these things together, which I believe I did in a similar way before, kind of what I'm saying is that I want the product of T and Y to be +1, right? That will cover both cases. So we want, putting it together, that the target value times the model value should be positive for all the patterns, right? That means that we've done exactly correct classification. If a pattern is misclassified, then this number is less than 0. I have to fix it, right? So this is kind of our goal. And kind of it suggests what our cost function should be. Our cost function is basically saying, my evaluation of how good a given set of weights is equal to, basically what I do is I want to add up all of the penalties, right? So I want to add up all of the misclassified data points. How far off is this number here? Right? For a misclassified point, this number is going to be negative, so I'm going to put a negative sign out here. And this is like saying, okay, if everyone is correctly classified, this number is 0. If there are some misclassifications, this number is positive, and it's kind of, positive in proportion to how bad this number is, right? So that kind of makes sense. And this is called the perceptron, cost function. So, this is just another way of representing an opinion about how good a given weight is, right? Just like for SVMs, for example, our cost function has to do with the margin, right? Trying to maximize the margin. For Fisher, we were trying to, maximize the, between class clustering or between class scatter and minimize the within class scatter. So this is just like another kind of cost function for doing learning, okay? But this one kind of makes perhaps a little more sense in the sense that we are just kind of scoring how badly did we do on the misclassified points, okay? And so how can we minimize this cost function? Well, I mean, you could minimize it with things like gradient descent and so on. But one thing that makes it very easy to minimize is this point-by-point method that we talked about earlier called stochastic gradient descent. So kind of the very simple idea that they came up with in the 1950s, this guy Rosenblatt, was that if this was my cost function, I could start with some initial W, some initial weights, and then I would evaluate point by point. If I'm correctly classified, don't do anything. If I'm misclassified, take a step along the gradient for that point. I just keep on doing that. So the function is super easy, right? So stochastic gradient descent one point at a time applied to this is super easy. This is like saying, for I equals 1 to the number of points, and I can permute the points. Probably don't just want to take them from 1 to n. Maybe I want to just do some sort of like, some random ordering of the points. I check and I ask, is this value greater than 0? If it is, that means that everything is good. This point is correctly classified, so don't do anything. Otherwise, I want to take a step along the gradient for that point. So that's like saying I'm going to take a step along the gradient just for this point. And let's call that EI, okay? And so this is like my step size, and this is my, gradient at point I. What is that gradient? Well, let's take a look at it. It's really actually very simple, right? If I look at this, here's my cost function. Taking the gradient of this with respect to W is just, this number times this vector, right? Super easy, because the gradient is just going to be this, right? So I can write this in a super simple way. And I guess there's a negative sign out here. So what this equals is W plus step size times phi x of n times Tn. And that's all it is. And actually, one way of thinking about this, which is really kind of a simple idea, is to say that, suppose that I'm looking at a point that has got target value 1, okay? And suppose my step size is 1, right? So this is like saying, if I have a misclassified point, then just add that point to W, right? If the point is misclassified the other way, if this number is negative, then I subtract this point from W. So it's kind of like adjusting the weight vector literally by the points themselves. It's a really simple idea. And so let me show you an example of how this works. So here is a simple set of points, blue dots and red dots. And you'll notice that this is not correctly classified, right? This is just like my initial guess, right? So what I can do is I can cycle through and say, okay, point number 1, which I've circled in pink, are you okay? If this point is okay, then I don't do anything. Point number 2, are you okay? Yes. Point number 3, yes, okay. Point number 4 is misclassified, right? This blue point should be on the other side of the line. And so what do I do? So this black vector that is pointing away from the solid black line, this W, this is like the W that I'm using that I want to update. I look at the vector that points to the point itself, and I am just making a new W by adding W plus that vector to arrive at a new value of W. And now when I draw the new line for that, it looks like this, right? That's all the update is just kind of like updating the weight vector by looking at the points. And now I continue my stochastic gradient descent cycling through the points. So now I look at the next point, point number 5. This point is okay, right? But now some of these points are not good anymore, but that's okay. So now I look at point 6. Point 6 is not great. And I do the same thing, right? I draw a vector that points to point number 6, and I add it to my W. That will kind of have the effect of tilting my line. And at this point, all my points are correctly classified, and I stop, right? So the perceptron updating algorithm is super simple. And so kind of what you can see here is that in a way what's happening is that when I have a misclassified point, kind of what I'm doing is I'm pushing the line to get that line more towards that point, right? So that's kind of like the intuition, is that I'm kind of pushing this line around to be closer to the points that I'm misclassifying. Because you can see that this black solid line, which is the discriminant, kind of rotates towards, towards that new point. And in some sense, maybe it overcompensates, but eventually by tilting this line back and forth, I get something that works. And so there is a perceptron convergence theorem that says that if the classes are indeed separable by a line, that this simple algorithm updating it will eventually find something that will correctly classify, right? And so it may take you, some long time, but it will converge in some finite number of steps to the right answer, right? So you can imagine that in 1958, this was pretty exciting, right? So it's kind of like you have this automatic thing that with a simple rule can divide the two classes. And when people talked about the perceptron originally, that's kind of what they were doing, was simple binary classification. So I'm going to say that, the perceptron convergence theorem says we eventually stop if the classes are linearly separable. So this is the perceptron, right? I always thought perceptron sounded like some sort of 1950s metal robot with perceptron. Anyway, so the perceptron is very limited, right? Like, it's not really clear, like, it may take a long time to train. There are definitely many solutions, right? So there's a question about, like, if there are many possible lines that do the job, which one will the perceptron find? It turns out that it's sensitive to parameter initialization. It's not really obvious how this will work for multiple classes, right? Like what happens then. But this simple idea is the core of modern neural networks. Okay, so now what I would talk about is kind of like the introduction of neural networks that uses this kind of simple basic idea of the perceptron. Okay, so let's write down that there's perceptron by itself is limited, right? One main thing that's pretty clear also is that, the model is still linear, right? So, the model is linear in the features, which means that I can only draw straight lines. It's not really clear how to make this work for multiple classes. Turns out to be sensitive to initialization and so on. So the key idea behind neural networks is to not just use one of these simple perceptrons, but to harness tens or hundreds or thousands of them into one big system and make them all work together. Okay? So neural networks are a way of basically assembling multiple perceptrons or perceptron-like structures in this kind of complicated parallel and series architecture to create, much more powerful classifiers or, to do regression and so on. So that's what I'm going to talk about next. So one thing that I should say up front, just as a, comment, is that, there's a lot of debate about what the word neural networks means, right? So, I think that it's fair to say that this is not how your brain works, right? So your brain is not a bunch of like perceptrons, right? I mean, your brain's got all these axons and dendrites, and no one really knows exactly how consciousness works in your head, right? So there have been kind of after the fact attempts to understand whether, you know, biological networks have any similarity to these kind of mechanical networks. But I guess that my personal opinion is they're two different things, right? So even though we talk about neurons, they're not like your brain neurons. It's just kind of like an analogy, okay? So what we're going to talk about mainly is called the multi-layer perceptron. Also known as MLP. So the first thing we're going to do is scrap this idea of this phi function, right? So let's go back to this original picture here, right? So the whole setup was that I have input data, x, and I've got weights, and then I had this phi, and the phi was basically an attempt for me to introduce some sort of nonlinearity into the problem, right? And it turns out that idea is extremely important, right? You need to have some nonlinearity in your network, but the problem was that I don't want, as a user, to have to figure out what should these transformations be for my data, right? So you guys have done on homeworks, for example, you know, if I asked you to do like a quadratic regression, then your phi functions are like, you know, 1x, x squared. But how do you know whether you should stop at x squared? Maybe you should have included x cubed. Like as a user, you don't want to have to make those kinds of decisions because you have no idea before you start training your network what the right answer is, right? So kind of the first idea is to, ditch these phi functions with the idea of letting the network kind of figure out good nonlinear transformations. In some sense, what a neural network is doing is it's discovering one big nonlinear transformation to map the inputs to the outputs. And so the setup is basically the following. So I'm going to just draw on a different piece of paper here. So whenever we start talking about neural networks, there's a lot of stuff to draw. So kind of the idea is that I have, I'm going to draw these little circles. These are like my input variables, right? So I have x1 through xd. So say I have a d-dimensional input. So we're going to call this the input layer. Right? So if I have a vector with d entries, these are the d entries, okay? So now what I'm going to do is I'm going to have what's called a hidden layer. And let's suppose that there are m units in my hidden layer. How do I produce these m units? Well, I'm going to basically have a linear function of each of the inputs going into this z, right? So kind of what I'm going to draw here is a bunch of straight line connections going into each one of these guys, right? I'm already regretting drawing this, but that's all right. So here, what's happening is that, each of these z's, well, let's back up and say for 1 second. So what does it mean when I have a bunch of lines converging at a node, right? So here, I'm going to draw this on a separate piece of paper here. What I'm going to say is that let's let AJ be from I equals 1 to D, something like this. So this is our old familiar linear function, right? So this J goes from 1 to M. This is like saying that at every one of these nodes up here, what I have is a basically linear function. These are, my usual weights. These are my biases. And this whole thing we're going to call, these are called activations. And then the z value here itself is where I introduce just a little bit of nonlinearity, right? So because so far everything is linear. And if I didn't have any sort of other thing, then combining a whole bunch of linear functions is just going to end up with one big linear function at the end, right? So where does the interesting part come from? The interesting part comes from taking the linear value that I get and processing it through some sort of a nonlinear activation function. Why can't I write activation function? Right, so for example, you remember the sigmoid from logistic regression, right? So we talked about how there's a function that looks basically like this. So one example that I could choose for h would be this nonlinear function. And there are other choices that I'll talk about in a second. So what I'm doing here is for every one of these nodes, I'm getting there by doing a linear combination of this stuff and then one final little nonlinear function here. And now I've got a whole bunch of new kind of values at these dots, right? Instead of having d values, this hidden layer may have a different number of dots. So now I have m values, right? And the critical idea is that now I think about this set of values as just being some other input that I could do the same thing again, right? So what I could do now is I could have another layer, and let's suppose we just call this the output layer. So here, this is an example of a neural network with an input layer, an output layer, and one hidden layer. And again, how do I get these numbers? Let's call these like y1 through yk. So again, how do I get these numbers? Well, I get them by doing the same kind of process, except on the outputs here, these z's, right? So instead, what I have is that, I have some b's. I sum up over, the m, let's call this j. I have, these j values from 1 to m, and I have another set of weights. These are different than these weights. These are, again, more activations, right? Except they're activations at the next layer. And then my output is, some other nonlinear function of these b's. So the idea is that I keep on doing linear combinations of the current stuff at one layer, and before I push them forward to the next layer, I apply this little nonlinear function, right? Again, if I didn't have these functions, then all these linear combinations would just result in one big linear combination at the end. There would be no nonlinearity. So these little simple functions, these h's and g's, are the way to introduce something new and interesting into the network, right? And so what I can do then is I can say, okay, well, how are each of these outputs kind of back related to each of the inputs? Well, I could just kind of write this whole function all together, right? I could say, okay, if I want to know what is, yk, what is yk? Well, it's g of bk. What is bk? Well, it's this sum. I have some weights going from the hidden layer to the output. And then I have these z's. What are these z's? These z's are, again, I'm plugging what I know here, h of these a's, right? So I can kind of make this whole, kind of nasty looking thing that explicitly relates the x's to the y's. And then I have the biases here, and I have the biases here, right? And so this tells me, okay, putting it all in one place, I've kind of collapsed it into one, complicated looking formula, right? And so how is this kind of network defined? So this set of weights, the wji's and the w primes, plus the biases, characterize the network. Right, so I could call this whole thing like W, right? I could say, okay, give me all of the little weights and biases and all the layers of the network, collect that into some big vector, right? And now kind of what I want to do is I have a cost function that says, how good is this set of all these weights? And I want to minimize this entire neural network over this cost function, okay? And so this is kind of the basic setup, right? And this is called a feed-forward network. Which, if I look at the picture of the network, that's why it makes sense why it's called that, right? So it's like saying I take, one set of inputs, I feed it forward to produce something in the hidden layer, I feed that forward to another hidden layer and another hidden layer until I get to the end, right? So I'm kind of pushing the input through the network to the right to produce the outputs, okay? And you can have as many of these hidden layers as you want. In fact, modern kind of machine learning networks have dozens or hundreds or thousands of layers, right? Which is kind of hard to imagine, right? The interesting thing is that actually, in theory, you don't need that many layers, right? So let me just say that in theory, two hidden layers are enough to create any decision boundary you want. But in practice, networks are very deep. And what deep means is it has many hidden layers. And that's what deep learning comes from, is how do I tune the many, many parameters at every layer of this massive neural network. So let me stop and ask, any questions or comments about just kind of like the main setup, right? So like, this is the main thing to understand from today, is what does this picture mean, right? Processing inputs by linearly combining them and applying some sort of a nonlinear function that I choose at every, node. In practice, what you'll find is that all of the, all the functions like this are the same per layer, but you may mix them up. And so there's a huge black art in terms of tuning, all the little meta choices you're making about a neural network, right? Should I use this function or should I use something else? Oftentimes it's just like whatever seems to work the best, right? There are some rules of thumb for what you should use for certain situations, but in practice, you as the user are playing around with the structure of the network, which nonlinear functions you're using, and you're seeing what works the best on your training data. That's just kind of like the way it functionally works. So, comments, questions? So today, we're not going to talk about how do I optimize the network, right? That's going to be the subject of Monday's lecture. So there's an algorithm called backpropagation that is used kind of endemically throughout machine learning in order to optimize these weights in a way that is really easy, but also kind of transparent to you as the user once you get going on it, right? So I'll teach it to you, but you're never going to really have to like implement it or like do it yourself. You're just kind of going to evaluate it, okay? So the big picture goal is, we basically, tune the large number of parameters which are like the weights and the biases at the various levels, in order to make the input come out to the output as close as possible, right? To make the inputs and outputs match what we see in the training data. Right, so we have some cost function, which again I can call E, and this W represents all of the parameters in the network, right? And so kind of what I want to just talk about for the rest of this lecture is like what is a good choice for this E of W, right? So we've talked about like both classification problems and regression problems. So let's just kind of talk about what would make sense for your cost function. And this is, again, nothing that's really new, right? So if we were trying to solve a regression problem, right? So for regression, this means that we're trying to predict a continuous number, right? So we're trying to drive the network output to basically continuous target outputs. So the natural choice is what we kind of already know, right? Our cost function for the weights should look like, something like this. This is like saying, I want the model output for a given set of weights to be as close as possible to the target output, right? And I want to minimize this. So that's like the most natural thing, right? So that would mean that at the very last layer of the network, for example, suppose that I was, looking at this example, then the G that I use for these numbers, maybe I'm trying to actually get these numbers to just match some target vector I have. So it kind of makes sense for the last activation function at this layer to just be like, don't do anything, just do the identity, right? Just whatever numbers come out of here, that's my prediction. Okay, so there's really no need for kind of a G at the end. This is like saying that, the last layer of activation functions can just be the identity transformation. Just take whatever the network gives you at the end. And so, one other thing to kind of like remember is that this thing basically came from also a probabilistic view of things, saying that if I have observations that are corrupted by Gaussian random noise, then this is like the maximum likelihood estimate thing to do, right? So in some sense, if I have this as my cost function, then I am kind of implicitly having this neural network learn a maximum likelihood estimate, okay? Okay, so this is if I'm trying to predict a number. What if I'm trying to do classification, X's and O's, right? Well, in that case, this doesn't make as much sense. And so if we're doing binary classification, then kind of like before, we have like, if I have class 1 with t equals, 1, and class 2 with t equals 0, then the natural cost function is this binary cross entropy function. So the natural cost function for how well I'm doing is saying I want to sum over all of the training samples, tn log yn plus 1 minus tn log 1 minus yn, right? So this is called the binary cross entropy. We already saw this in the lecture on logistic regression, right? Why is this good? This is like saying, okay, I want to minimize this cost, right? So if, and I want to drive the y's to be equal to the t's. So this is kind of like saying that, remember that log 0 is equal to 1, and log 0 is equal to minus infinity, sorry. And log 1 is equal to 0, right? So it's kind of like saying that, if this number is 1, then I want to drive this number to be 0, right? To make this number small, right? And kind of vice versa. If this number is 0, then this thing here I want to be active, and then this is going to drive the yn to be equal to 0, right? So I'm kind of trying to make this work in such a way that the t's and the y's kind of match up. And the idea is that the interpretation of the y vector is basically, you know, 2 probabilities that add up to 1. And so kind of what I want is that the output, in some sense, kind of gives me the probability that I can interpret to be the probability being in class 1. So kind of like the idea is to interpret, or maybe actually, maybe a better way of saying this is to interpret the output y as the probability that I'm in class 1. So I kind of have a network that looks like, you know, I have a network that has all these inputs. I have a bunch of hidden layers. And then I kind of come down to one node at the end. And this node I could think of as kind of telling me, you know, a value in 0, 1 that tells me how likely I am to be in class 1, right? And so for me to get from whatever function or whatever number feeds into this node, I had to convert that into a probability in the range of 0 to 1, right? So, you know, the last activation function should be like a sigmoid, right? Remember, the sigmoid is this function that looks like, you know, this. And the function itself is 1 over 1 plus e to the minus b, right? This is like saying that if I plug in minus infinity, I get 0. If I plug in b equals 0, I get 1/2. And if I plug in b equals plus infinity, I get 1, right? So this is a way of mapping any real number into a probability. And so this kind of makes sense as the last kind of function on the road, right? Another thing that I could do if I wanted to do it slightly differently is I could do like a step function, right? So I could do a sine function like we were talking about with the original perceptron, where I could just say, give me the sine of the output. So one thing that's kind of important is that in order to optimize all these parameters, it turns out that it's really useful or critical in some sense for all of the stuff inside this neural network to be differentiable, right? So, you know, the nice thing about this function is this is something that I can actually take the derivative of, which means that I can actually do gradient descent on this whole thing, right? If I have something where there's some discontinuities or something like that, then I could have a big problem with taking derivatives, right? So as we'll see on Monday, we want to be able to apply gradient-based methods to minimizing the subjective function, and hence everything that we put in here hopefully is going to be differentiable, okay? And then finally, the last thing that I might want to do with my network is multi-class classification, right? So instead of coming down to one single number for interpreting it as a probability of which class I'm in, maybe what I want to do is I want to do like k-class classification. So if I do like multi-class classification, like let's suppose I have, you know, k classes, then the cost function that I want to use is the one that we talked about again for logistic regression, and the same one I asked you about on the exam. This is like saying I look at the target value and I look at the value of the outputs at the final layer. So again, only one of these is not equal to 0. And that's the kind of situation where what I want to do is I want to have, my network blah, 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 blah. And what comes out of this network maybe, so say that, say I have a 3-class classifier. What I want this to be here is like a vector that sums to 1 and can be interpreted as the probabilities that I'm in each class. So this is like the probability of being in the kth class. And so for this, what is the natural kind of like activation function at the very end of the network? That activation function should be the softmax function, right? Which we talked about before, and we had it on the exam, where I want to take any vector that comes out, and I want to normalize those guys to be basically summing to 1, right? So this is like saying that, the output activation function is naturally a softmax function, right? Just to remember how that works. That's like saying that if I have, if the last layer should basically be like taking all of the inputs, all the activations that are coming into that node, and normalizing them in this way. So this is going to satisfy that all the elements are going to be between 0 and 1, and all of these k numbers are going to add up to 1, right? And so, again, that kind of makes sense for multi-class classification problems. So in a way, when you set up your neural network, you should think about, okay, what is the desired output? Is it a real number? Is it a single probability? Or is it a vector of probabilities? And that will define what, at least at the very end, your activation functions should make sense of being, right? And again, the nice thing about this is nice and differentiable according to the W's. So again, we haven't disturbed the ability of our network to do differentiation. And so overall, we have some, super complicated but differentiable cost function. And it's also highly nonlinear because buried in this cost function are all these sigmoids and stuff like that are causing the input variables to not be combined linearly. I mean, the softmax itself is also definitely very nonlinear, right? And so the big challenge then is, how do I actually minimize this function, right? So, how to actually minimize this? Well, it's complicated, right? Because there are lots and lots of kind of weird, symmetries and so on in the cost function. Like I could just kind of like rename neurons, and so put it this way: there are lots of values of the weights that will give me exactly the same value of the cost function, just because of like changing, putting a positive sign or putting a negative sign here, a negative sign here. I've got the same values, but a totally different, set of weights, right? So there's like many, what I would call, what's the word? Many values of W have the same E of W due to, symmetries. So we had to kind of find a way to get around that. But, the key idea is, what's called backpropagation. Or backprop. And that's what we're going to talk about in detail next time, is how could I possibly hope to minimize all these variables at all these different layers of the network? Well, it turns out that there is a way to do it in this kind of like clever recursive way, where I kind of mentioned this concept before of, to evaluate the network, we use this feed forward system. To minimize the network or to optimize the network, we use what's called a feedback system that is basically taking stuff from the other end of the network and pushing it back through all the way to the weights at the very top layer of the network. And so that's called backpropagation. So we'll talk about that in a lot of detail next time. And again, like I said, we kind of only focused here on what should you be doing at the output layer of the network for the type of problem that you have. That doesn't really address the question about like when you have a, so intermediate nonlinear activation functions right? We kind of talked about, the sigmoid is a possibility. There's something called the tan-H hypertangent or a hyperbolic tangent function. That's a function that kind of looks like the sigmoid, but instead of going from 0 to 1, it goes from -1 to 1. There's also something called the ReLU, which stands for rectified linear unit, a fancy name for a function that just looks like this. And so, again, how do you choose what you should be doing in the middle of your network? Well, honestly, it's very trial and error-y, right? And so one thing I'm going to have at the end of this set of 3 lectures is a panel. So two weeks from now, I guess it's going to be not next week, but the Monday, I'm going to have a panel of grad students come in and kind of show you how they use machine learning in general, but also neural networks specifically in their research, and how easy it is to set up a neural network and try different activation functions and see what the answers are, right? And modern packages make it so easy just to kind of like play around with ideas until you've reached the best area that you can get on your training data. So that's going to be something where I have real grad students coming in to talk to you about what they do for their research. And so I think that should be interesting. And the other thing is that there are all sorts of things about like, the way I drew these networks is as if every neuron at one layer is connected to every neuron at the subsequent layer. That's called a fully connected network, and that's often the way it works, but it doesn't have to be this way either. You could have like missing connections and stuff like that. So when we talk about the deep learning stuff, we'll talk about ways of modifying this structure in different and interesting ways where not everything is fully connected. So I guess the way I drew this is what's called fully connected, but it doesn't have to be. Okay. And so, like I said, we're kind of reaching the limit of what you can work out by paper and pencil on a homework problem or on an exam, right? And so when I put together the next homework, when we're using neural networks, I may, although I haven't figured it out yet, just have you use like a backpropagation package and train neural networks on things and play around with using different activation functions instead of actually asking you to code it from scratch. I don't think there's really a huge benefit to asking you to write your own backpropagation algorithm. That's like a kind of a pain, right? But that's where we're going. And so again, this is probably like what you think of, or what people think of when they think about machine learning is neural networks, right? So that's kind of why we're kind of getting to this point. Okay, so questions or comments about anything? All right, so let me stop the recording.